I'm going to go ahead and start by introducing our guest speaker for today. So today's talk is The Art of Dynamics, and it's going to be presented by David Levinson. David Levinson has 46 years of experience as a dynamicist in the space industry, where he has been responsible for producing special purpose computer programs for predicting motion of complex mechanical systems. And currently works in the Dynamics and Controls Analysis, or DCA group at Maxar Space Infrastructure, which was formerly known as SSL. Most of you might know it, since 2013. It's a great place to work. And so over the years, Dave Levinson has received a number of recognitions and awards, such as the AIAA San Francisco Section Outstanding Young Engineer Award, and the Section Engineer of the Year in Astronautics, and the Section Engineering Educator of the Year Award, and other awards from ASME as well. Currently, Mr. Levinson is a fellow of both the American Astronautical Society and ASME, American Society of Mechanical Engineers, and an associate fellow of AIAA. Participates in a lot of Discover K through 12 engineering outreach programs for over 20 years, and has given many classroom presentations, and of course has numerous publications. So you can read the whole bio on the event page, but we were going to go ahead and get started with the presentation. So thank you, David, and we'll let you get started.
How do you do? This is a repeat of a talk I originally gave on April 26, 2020, here at Santa Clara University to the graduating seniors in mechanical engineering at the request of Professor Ayubi, who had spent his sabbatical working in my department at Maxar Space. He had asked me to inspire the students to consider careers in dynamics by explaining to them how I became a dynamicist. As I began preparing the talk, I soon realized that because the only exposure the students had to the field of dynamics was a one-semester required introductory course in the subject, and likely no course whatsoever in the history of science or even the history of Western civilization. I needed to put modern dynamics in its proper historical context for the students, which I did. That historical background, combined with my own story, became the talk that I gave to the Santa Clara mechanical engineering students in 2020 and will now give to you. So as you can see, the title is The Art of Dynamics, and I put an asterisk by art because there's lots of definitions of art, and I wanted that one, an occupation requiring knowledge or skill. So I'm a dynamicist, and that immediately should raise the question, like how do you get the thing to advance? What is a dynamicist? And if you look it up in the dictionary, a dynamicist is any person who studies the branch of mechanics concerned with the motion of bodies under the action of forces. Now, I take issue with this definition. I don't think it's a very good one because of the word studies. So here you see somebody sitting in the library surrounded by dynamics books, studying his head off. And you mean this is all a dynamicist does, studies. You know, there's got to be more to it than that. So I thought that was a bad definition and I needed a better one. So let's get down to fundamentals. What is the purpose of dynamics? The answer is to predict, not to explain. You know, physicists are always trying to explain things. That we don't predict things, explain things, we predict them. Given forces acting on a system, predict its motion. Given the motion of a system, predict the forces that are causing it, or a combination, a mixture of the two. And now says who? You know, why should you think that's a good definition? Well, I'm going to start off with a quotation. And the quotation is, in this sense, rational mechanics will be the science of motions resulting from any forces whatsoever, and of the forces required to produce any motions accurately proposed and demonstrated. So you say, okay, big deal. It's a quotation, but let's see who it made it. It's Isaac Newton from the preface to Mathematical Principles of Natural Philosophy, which he published in 1687. And this is known as the Principia, as it's in Latin. It was written in Latin, and it's called the Principia. So who am I to argue with Isaac Newton? So that's going to be our official definition. Now, what does one need in order to do dynamics? The answer is that one needs the skills to formulate correct equations of motion of any system of interconnected bodies. And well, why? Why is that what one needs? Well, because without correct equations of motion, there is very little meaningful work one can do in dynamics. But with the correct equations of motion, one can do almost anything in dynamics. Now, the problem is that most university courses of instruction in dynamics fail to teach students how to formulate equations of motion. The most important thing they should be learning is not even covered. I would bet everybody in here has had a dynamics course, and I bet you they never even devoted a single lecture, let alone the months it takes to learn how to do this. So that's a bad definition here. And the better definition is a dynamicist is someone who has mastered the skills required to formulate correct equations of motion of systems of interconnected bodies. So that's going to be my definition. And however, this has not always been the case. So if we go, I'm going to do a history of dynamics, the entire subject. And I do mention it's condensed. Now, there are several historical periods in dynamics, and the one that exists from antiquity to the year 1543, I call the age of explanations. And I'll explain what I mean by explanations. First of all, every important scientific question asked from the 3rd century on was originally asked by the Greeks. And nobody knows why science arose in Greece. There have even been science fiction stories about aliens with advanced technology landing in Greece and teaching them this stuff. But there are other more plausible explanations. One of them being that in Greece, that their gods were not all powerful and omnipotent, and the Greeks were not that afraid of them. Whereas in places like Egypt and Mesopotamia, there was only so far they would go to ask questions about the universe or nature. You know, they didn't want to invoke the wrath of these all-powerful gods. But in Greece, I mean, if you read Greek mythology, the Greek gods are just like humans with superpowers. You know, they're not these omnipotent creatures. So that's there's other explanations. But anyhow, science started in Greece. And Aristotle was the first dynamicist, and he undertook the first systematic study of celestial and terrestrial motion. He wrote many books, but the two we're going to be concerned with here are the ones that have to do with dynamics. And De Caelo is the Latin name for On the Heavens, and Physica is the book he called Physics. So that's those are the two books he wrote. Now, what's interesting is that these are major works on cosmology and terrestrial dynamics, and these are words, there's no math. Even though the Greeks had a highly developed geometry, they had hundreds and hundreds of theorems they've proved on plane and solid geometry, but these works only had words in them. Now, I'm going to lay out the basics of Aristotelian dynamics. The laws that govern the motion in the heavens are different from those that govern motion near or on the earth. To each thing there corresponds a natural place. Objects tend to move to their natural places. The natural place of the center of the earth is at the center of the universe, and heavenly objects move in perfect circles around the center of the universe and hence about the center of the Earth. There is a distinction between natural motions, like the falling of heavy bodies, or the motions of the planets, and violent motions, like throwing a spear, a projectile. And heavier bodies fall faster than light ones. And this is a quotation from Aristotle: if a weight falls from a certain height in so much time, a weight which is twice as great will fall from the same height in half the time. And natural motions take place without forces. In other words, things in the heavens orbit in circles, but there are no forces involved. But motion, violent motion, like throwing a projectile, cannot take place without the application of force. When the force is removed, the violent motion ceases. So as soon as my hand loses contact with the spear, it will stop moving forward, but it will fall because that's a natural motion. You see, so that that's the substance of Aristotle's dynamics. Now, you might notice that every single thing is wrong. There's not a single right thing there. So why do we revere him? Well, there's a saying, you can't beat something with nothing. There's in other cultures, in other places in the world, nobody even came up with anything, even the wrong stuff. But when you have something very specific, like if a weight falls from a certain height in so much time, a weight which is twice as great will fall from the same height in half the time, you can test that. And the people were saying, well, hey, this doesn't sound right, let me test it. And that's how it began. So the fact that he said all of these wrong things was something that nobody else had ever done anywhere. And so by building on that, and that still goes on. You know, we have theories in physics, and people come along and say, hey, that doesn't look right, let's try something else. Well, you're not going to say the guy that got it wrong, it was a failure, because he did that. You know, that's the way progress takes place. So this was really important. Now, this was so convincing that Aristotelian dynamics remained unchallenged for almost 2,000 years. Imagine that. That theory hung around for 2 millennia. Now, I'll give you an example. During this same period, we're way up to the year 1300, there was a famous dynamicist named John Buridan, who was the world's foremost authority on falling bodies. And he wrote this in a book about falling bodies. It says, from this theory also appears the cause of why the natural motion of a heavy body downward is continually accelerated. For from the beginning, only the gravity was moving it. Therefore, it moved more slowly, but in moving, it impressed in the heavy body an impetus. This impetus now, together with its gravity, moves it. Therefore, the motion becomes faster, and by the amount it is faster, so the impetus becomes more intense. Therefore, the movement evidently becomes continually faster. All right, now this is everything you ever wanted to know about falling bodies, but there's something terribly wrong with it. And what's wrong with it is it's tautological. Now, for those of you who don't know what a tautology is, it's the verbal equivalent of an identity in mathematics. For example, if I say to you, if you don't improve, you'll never get any better. I really haven't said anything. I'm just going around in circles and using different ways of saying the same thing. For example, back some years ago in 1979, America's first space station was about to fall. They were planning to go up and boost it with the space shuttle, but it never got off the ground until 1981. So this thing was going to fall, and everybody was worried about where it was going to fall. Well, here's this theory of falling bodies, and it doesn't have the capability of even addressing this question. You cannot find out where Skylab will fall by using this kind of dynamics. So this whole period had stuff like this, which was not very useful, but it gave people something to build on. So this was very important in the history of science. Now, the most important period in the entire history of science for the human race occurred between 1543 and 1687, and it's called the Scientific Revolution. Now, I'm going to read you a quotation. In the 16th and 17th century, the intellectual map of Europe underwent the most profound transformation in the whole history of Western civilization. This upheaval has been given the name of the scientific revolution, and it is the fountainhead of our modern scientific and technological society. It was, of course, as well, the culmination of the scientific and philosophical traditions of antiquity, the Middle Ages, and the Renaissance. Everything seems to have flowed together in this period to produce the creation of modern science. It is a unique event, having never occurred in any other place or time, and its effect on the development of Western civilization ranks it among the greatest events of human history. So in this 144-year period, was the most important thing for us as engineers, because this is where it all started. And I'm going to go through some of the important figures during that period. Now, this quotation comes from this book. L. Pierce Williams wrote a 3-volume set called The History of Science in Western Civilization. It's a 3-volume set. And if you can get it, it's probably out of print, but you might be able to get it on the internet. The second volume, the whole second volume, is devoted to the scientific revolution. And what's so good about it is that there's a lot of original source material, lots of English translations of very fundamental things that all the big names in this period wrote. It's not just Williams' commentary, but it's got the original source material. Steffens was his graduate student at Cornell, and he went on to become a history professor at the University of Vermont. So if you really want to read there are hundreds of other books on the scientific revolution, but this one is I particularly like. Now, the central problem of the scientific revolution was the problem of motion as it applies to the heavenly bodies. Now, the question is, why did Europeans have such a great interest in astronomical calculations? Well, the first reason is astrology. The Black Plague, which killed 30 to 60% of Europe's population, and that's 25 to 30 million people. I mean, you think that our pandemic was bad. This, you're walking down the street and every other person died. And there were particularly vicious wars of the 14th and 15th centuries. And this fostered a belief in demons and the supernatural. So people turned to the cosmos for answers. And to determine celestial influences on someone's life, astrologers needed to be able to calculate precise positions of the planets and stars at the moment of the person's birth. And this is still true. I don't know how many of you have talked to real astrologers, but they use the same kind of computer programs we use in the space industry to calculate orbits. They take it seriously. And because they take it seriously, they use the best software they can possibly get to calculate where the planets and the stars and everything is going to be. What they do with that information is subject of debate, but they always start off with the good stuff because they take it seriously. So if you're going to talk to an astrologer, you better believe they know what they're talking about when they do with the celestial mechanics. Now, European exploration of the world in the 15th and 16th centuries required precise navigation, but navigational instruments were extremely primitive. And in the 16th century, the calendar was out of whack, and Christian Europe needed to know the precise date of their most important holiday, which is Easter. And inaccuracies in its determination led the church to back improvements in astronomical calculation. This problem of finding out when Easter occurs, it was so difficult, it was given the Latin name computus, which means the computation. And it's still a difficult problem. If any of you need a term project, I'm serious. And to make it a fair game, no electronic calculation is permitted. You got to use paper and pencil or a quill pen and parchment if you really want to get tough. But for a science fair project or a term project at college, this is really tough. Now, why is it tough? Well, Easter is connected to Passover, which is based on a lunar calendar, and the normal everyday calendar is the solar calendar, and those two systems are incompatible. So trying to find out when Easter is a very difficult mathematical problem. And after you go home, look up Computus and you'll see what I mean. But I think that if anybody's looking for a term project, there it is. Now, finally, there was a titanic struggle between the Catholic Church and the Protestant Reformation. And attacks by the scientific revolution on Aristotelian science affected the theological foundations of Protestants and Catholics in different ways. All of their theology was based on Aristotle. Remember, he'd been around for 2,000 years, his influence. And so what happened is as parts of the Aristotelian science got discredited, it affected these two branches of Christianity in different ways. And what happened was they were all anxious to study the science to find out what the truth was, because this was a major theological issue as well as scientific. Now, let's look at what they were dealing with. So here are the orbits of celestial bodies about the Earth. If you look at on the left picture, the blue dot, the light blue dot in the middle is the Earth, and the dark blue orbit is the orbit of Venus, of Mercury about the Earth. The green orbit is the orbit of Venus, and the red one is the orbit of Mars around the Earth. Now you can see those are pretty complicated orbits. And if you look at the outer planets, the sun goes around that little red circle on the right plot, and Jupiter is the green orbit on the right plot, and Saturn, which is the last planet they could see, was the blue orbit. Now, this caused some problems because there's retrograde motion. If you look at if you look here, you can see that, they're in this plane. They're just looking out this way, and they see, let's say they see Saturn moving this way, and then it switches directions. It moves back. See, as it does that, it comes back, and then it goes the other way, and then it switches directions again. So they're looking up, and they see these planets moving along like this. Whoa, what's going on here? And the philosophers and the clergy said the heavens are perfect, circles are perfect, therefore motion in the heavens must be circular. Well, does that look like a circle? No. So how did they deal with it? Well, they did. They managed to deal with it. This is what they did. They created this big circle called a deferent, and the Earth is at this point right here. So the center of the deferent is called an eccentric, and it's right here. And the Earth is located at a distance d away from the eccentric. Now, on the other side, at the same distance d, is another point called an equant. And then they had another perfect circle up here whose center moved on the deferent. And the circle here was called the epicycle. And the line that goes from the center of the deferent to the center of the epicycle, it remains constant. And the angular speed of the line that goes from the equant to the center of the epicycle, that angular speed remains constant. Now, if you put all of that together, it generates that red curve, which looks amazingly similar to what's going on there. So with these circles, they were able to generate these orbits. And by picking the D and the R and the omega just right, they could get very accurate predictions of what was going on in the heavens. And so the astronomers said, well, the astronomical calculations with circles are messy and difficult, but accurate enough. Now, the geocentric mathematical model of the universe is due to Ptolemy, who lived circa 100 to 170 AD. So they worked out all this mathematics back then, which is really impressive. I mean, if you've ever seen the math on this, it would test anybody who, even engineering students with advanced degrees. It's very difficult. Now, this changed in 1543. on his deathbed, he finally got his book published called, it's a famous book called De Revolutionibus. And it's on the revolutions of the heavenly spheres. And there's the front page of it. And what he did is he said, okay, if we put the sun at the center, the calculations get easier. So this book contained the mathematical theory and astronomical data that form the basis of the heliocentric Copernican theory. I mean, it's got all the mathematics and everything, showing that you could use this model and you could also calculate where things were in the heavens. And he replaced the equant with more epicycles. But this was not any more accurate than the geocentric model. So they're about the same, but it was a lot less work. You know, it was easier to use. And the only person prior to Copernicus to have seriously considered the heliocentric theory was the Greek astronomer Aristarchus of Samos. Now, by heliocentric theory, I don't mean some guy walking down the street and saying, hey, maybe the Earth isn't the center of the universe. Maybe the sun is. That's not what I mean. I mean doing all the work, the calculations to show that everything fits. That's what these guys were doing. That's why they're given credit. Now, Galileo came along and published lots of books, but the one we'll be dealing with is the dialogues concerning two new sciences. And you can get the English translation of this. I've read it. And the two new sciences are strength of materials and projectile motion. Now, he lived in a period where you could get burned at the stake if you were politically incorrect. And so he had to watch. There was a contemporary named Giordano Bruno who got burned at the stake. He was a cosmologist, and he said some things the establishment didn't like about the heavens, and he got burned at the stake. So Galileo said, well, you know, maybe I better not do this the way he did it. So he wrote these dialogues. You know, it looks like a play, the way these characters. And there were three characters. There's Salviati, who was actually Galileo. You know, but it was this character. He never called him that himself in the book. He had this character, Salviati. And then there was a guy named Simplicio, who was the establishment Aristotelian. And then there was Sagredo, who was named after a friend of Galileo's. And he was sort of initially neutral. And of course, he came around as the book goes on to thinking like Galileo did, because Galileo wrote the book and he could make the ending come out any way he wanted. Well, the first thing Galileo did is replace the Aristotelian cosmos with S equals 1/2 GT squared. And those of you who are engineers will recognize S is the distance a body falls from rest in time T. And and remember, Aristotle said heavier objects fall faster than light ones. And notice this does not contain mass. So it doesn't matter what the mass is, you get the same answer no matter, you know, for a heavy body as a light body. And it was demonstrated on the moon in one of the Apollo missions when they dropped a feather and a hammer, and with no air resistance, they hit the ground on the moon at the same time. The circular inertia, he said things move naturally in circles unless they're acted upon by other forces. And something we're all familiar with is the parallelogram law for addition of forces. Everybody's had that in mechanics. Well, he invented it, or discovered it, as people like to say. Anyway, and then came Tycho Brahe, who was an astronomer, and he was regarded by many historians as the greatest observational astronomer who ever lived. And here's what he did. The instruments that Tycho designed and built enabled him to make measurements of unprecedented accuracy of the positions of the planets and stars 20 years prior to the invention of the telescope. His measurements of positions of Mars were accurate to within 2 arc minutes. That's 1/30th of a degree. He did it without a telescope. And it was his high accuracy that enabled Kepler, who was Tycho's assistant, to make his landmark discoveries about planetary motion. Tycho gathered such accurate data to support his theory that the planets orbit the sun while the sun orbits the Earth. He was trying to get evidence for something that wasn't true, and he needed really accurate data to do that. And so that's why he was motivated to do it. And so then we come to Kepler, and here are some of the books he wrote on astronomy. And this Astronomia Nova is to do astronomy. And so Kepler was really getting down to the nitty gritty here. The first, he has three famous laws. The planets move in elliptic orbits with the sun at one focus. So if this is the sun, and here's one planet, here's planet P1, orbits the sun in an elliptic orbit, and this is the focus of that ellipse. And planet P2 orbits the sun in a different ellipse, but it has the same focus. So that's his first law. And the line from the sun to each planet sweeps out equal areas and equal times. If you look at this planet, if you look at how far it moves in a time delta t, it sweeps out this sort of pie-shaped region, and it has an area. And then later on, during the same time period, delta t, it sweeps out a different looking region. But he showed that the area of the second one is equal to the area of the first one. And then in this famous square cubed law, the period, the amount of time it takes to go around this orbit once is T1, and the amount of time it takes to go around here once is T2, and the semi-major axis, half the longest length of the ellipse, is related to the square of the period divided by the cube of the semi-major axis is the same for all the planets. So he got that right. Now, this is all, he used the position measurements of Mars from Tycho's data to determine that the orbit of Mars about the sun is an ellipse. Mars had the most eccentric orbit in the solar system, so it made a good candidate for doing the study. And Tycho's data were more accurate than anybody else's data, and those extra decimal places were what enabled him to see all of this. And his calculations covered 900 folio-sized pages in small handwriting. Now, this is a tribute to the character of Kepler. And can you imagine if he had said, oh man, after 850 pages, I've had it, let's let it go, let it slide. But he didn't, he did the whole thing, and he was able to come up with these laws. Now, you should notice, though, that they eliminated the need for epicycles, deferents, equants, and eccentrics, because it really got simple now. But notice that these are kinematical laws. There's no forces or anything. It's just observations mathematized. So this is that. So that brings us to René Descartes. You've all heard of Cartesian coordinates. That's named after him. He invented coordinate axes and that kind of thing. Now, he could not accept the concept of action at a distance, for example, gravity or magnetism. And he rejected the concept of a vacuum. He believed that motion was impossible in a vacuum because there would be no objects to push against. And he thought that the solar system was filled with ether, and that vortices in the ether were responsible for the motions of the planets. And he almost got the concept of inertia right. He said bodies remain in motion or at rest unless acted upon by other bodies, because of course there couldn't be forces that didn't make contact. And he was probably the single most important influence on Newton. And again, you notice he's completely wrong on everything. But this caught Newton's eye, and it made him study this. You see, these guys who got stuff wrong were very important in the history of science, because the other people didn't get anything because they didn't do anything. So this is what made him famous. So that brings us to the greatest one of them all, is Isaac Newton. And the Principia, published in 1687, is considered the greatest scientific work of all times. And that is what he is in there is he, first of all, he has the idea of an inertia. He says there exist reference frames, and things move in straight lines in these reference frames at constant speed, and or stay at rest unless acted upon by forces. And then the famous F equals ma that if you have a particle and you apply a force to it and it has a mass m, it'll accelerate a, and they're related by that equation. And then he had the action-reaction. If I push on you with 5 pounds of force, you push back on me with 5 pounds of force, and there's nothing you can do about it. That's just what it has to be. And then he came up with the law of universal gravitation. The gravitational force between two particles is equal to the product of their masses divided by the distance between them squared multiplied by the universal gravitational constant. And then he had to do all this, he had to invent calculus, both integral and differential calculus. He had to invent the differential calculus to get the laws of motion, and the integral calculus to prove that the gravitational force exerted by a planet on a particle is equivalent to a particle being placed at the center of the planet and having the mass of the planet. You have to use calculus to prove that. But there's no calculus in the Principia. He didn't think he could spring all of this new physics on him, on the population, based on new math. So he redid all of it with geometry, because geometry had been around for 2,000 years, and he thought people had a better chance of accepting it, and he was right, but it makes everything really complicated. But in private, he figured out everything with calculus, and then got the, once he knew the right answer, he would published it with the geometric proofs. Now, there are 3 books in the Principia. The first book has Newton's laws of motion. The third book has the universal gravitational constant. The fluxions, the calculus is not in there. And the book 2 is devoted to wiping out Descartes. You know, Descartes had all that bad stuff, and that's what happened. And he's responsible for the Newtonian synthesis. Newton united heaven and earth, showed that the same laws exist for both heaven and earth, which was completely the opposite of what Aristotle believed. Now, this is a chart I made up, because you often hear the Copernican revolution and the scientific revolution used interchangeably. But what really happened is it started off with astronomy and cosmology when Copernicus published De Revolutionibus, and it ended in 1687 when Newton published the Principia. But it spilled over into the other sciences as time went on. And so we have the scientific revolution, and that's just the way it seemed to me. So I made that figure up. I don't think anybody else ever drew it that way. But if you want to read, there's lots of books about the scientific revolution and the Copernican revolution. That's a very good book by Thomas Kuhn. I recommend it if you're interested. Now, Scientific American reviewed it. They said it was an illuminating account of the intellectual transformation which laid the foundations of modern science and philosophy, and which may therefore be said to have created the modern world. So it got pretty good marks from Scientific American. Now, this brings us to the age of analytical generality. It began with Newton's Principia and ended in 1957. The first part of that is called the Enlightenment, began with the publication of the Principia and ended with the French Revolution. You know, it was not very enlightening to be chopping people's heads off in the town square. So that is the end of that. That was, the Enlightenment is also known as the Age of Reason, where all of this scientific stuff spilled over into other areas of human knowledge, like politics and philosophy and so on. They got the idea that reason could be used in non-scientific areas. So here's the, we're all familiar with Euler. He was one of the analytical generality people. He's the father of rigid body dynamics, and he was one of the 4 greatest mathematicians in history, Archimedes, Newton, and Gauss being the other 3. And he was the most prolific of all mathematicians. There's if you look on the internet, there's an Euler archive where they have all the translated works of his, and they still haven't finished translating all of them into English after, you know, more than 2 centuries. So he just published a lot of stuff. And as engineers in the aerospace business, we know about Euler's kinematical equations, Euler's dynamical equations, Euler angles, Euler parameters, and Euler's theorem on rotation. So we deal with them almost every day at work. And then there was D'Alembert. Those of you who have studied freshman mechanics might have had it presented to you as D'Alembert's principle, where you apply minus ma as a force, an inertia force to something, and then you, along with the active forces, and then you can treat the system as like a statics problem, and the output from that is the equations of motion. Well, D'Alembert is the inventor of D'Alembert's principle, which is an amazing coincidence. Now, Lagrange, some of you have seen Lagrangian mechanics, and he was famous enough to get his own postage stamp. He published Analytical Mechanics. So Lagrange is a famous guy. And then there's Hamilton, and he's known for Hamilton's canonical equations, Hamilton's principle, and quaternions. Hamilton thought quaternions was the most important thing he ever did. And it actually wasn't. If it hadn't been for the space business, people wouldn't even have heard of them today. But he developed them, and he thought that was the best thing he had ever done. But he was a very famous mathematician, and he figured out the last piece of the puzzle while he was walking across that bridge near Dublin. And he carved those equations, I squared equals j squared equals k squared equals ijk equals minus 1 on the bridge. Now that's all been worn off by the passage of time, but they put a plaque on the bridge. If you go there now, you can see this plaque, which it honors Hamilton. So, and then, now if we go back to Lagrange for a minute, in the preface, he says, there already exist several treatises on mechanics, but the purpose of this one is entirely new. I propose to condense the theory of this science and the method of solving the related problems in general formulas, whose simple application produces all the necessary equations for the solution of each problem. No figures will be found in this work. There's not a single drawing in the book. The methods I present require neither constructions or geometrical or mechanical arguments, but solely algebraic operations subject to a regular and uniform procedure. So he thought he had it all solved there. And Mach, Mach number, that guy, he said analytical mechanics was brought to its highest degree of perfection by Lagrange. Lagrange's aim is to dispose once and for all of the reasoning necessary to resolve mechanical problems by embodying as much as possible of it in a single formula. This he did. Every case that presents itself can now be dealt with by a very simple, highly symmetrical, and perspicuous schema, and whatever reasoning is left is performed by purely mechanical methods. The mechanics of Lagrange is a stupendous contribution to the economy of thought. Now, it turns out that everybody has seen this, or anybody's not. These are Lagrange's equations. But the problem is, this is a lie. Every case that presents itself can now be dealt with by a very simple, highly symmetrical, and perspicuous schema. And in practice, this isn't true, as we have discovered. And that brings us to the present age, the age of simulation, which began in 1957 with the launching of Sputnik, and about the same time the digital computer became into widespread use until now. Now, the main problem in the age of simulation is what's called the initial value problem in dynamics. So what is it? Well, let's say here's a dynamical system, and like a satellite. And I don't mean to imply that this is an exact drawing of a satellite we built at Maxar, but what you're given is a mechanical system. You're given a complete description of the geometric and inertia properties of the system, and you're given a description of the forces acting on it. So we have these F1 and F2 or thruster forces. We have a torque on a rotor, a distributed force on a solar panel or a boom, and a robotic arm. You can have all of that. So you're given a complete description of its motion at t equals 0, and you're asked to find the what happens when t is greater than 0. That's the initial value problem. Now, the solution of the initial value problem is in two parts. The first part is to formulate equations of motion, and the second is to solve the equations of motion. Now, this is an ordered pair, which a lot of people tend to forget. And this is not an issue because we just do numerical integration. We use a computer. So that problem is not an issue, but this is a major issue. And why is it a major issue? Because the first task can complicate matters to such an extent that the second task cannot be undertaken at all. And you cannot solve non-existent equations. That's something you have to remember. So in principle, you can always get equations in motion using just about any method, but in practice, you can't. So this is an important fact to keep in mind. And that brings us to Thomas Kane, who is the most significant dynamicist of the 20th century. His famous equations are FR plus FR star equals 0. FR is called a generalized active force, a scalar function, and FR star is a generalized inertia force. These are scalar functions. And there's one for each degree of freedom. It says n degrees of freedom. Now, he realized that the classical methods were inadequate in practice for formulating dynamical equations of motion in complex mechanical systems. But prior to the space age and the advent of computers, it was unlikely that anyone would have attempted to formulate equations of motion of a complex system since there was no possibility of solving them. So the shortcomings of the classical methods remained undiscovered until the 1960s, when the space age created the need for such equations. Finally, people started trying to formulate them, and they said, oh, we got a lot of problems here. And so Kane's method for formulating dynamical equations of motion revolutionized dynamical analysis of complex systems of interconnected bodies. Now, in more recent history, in the 1970s, a controversy arose surrounding which was the best method for formulating equations of motion. And it stemmed from the failure to distinguish principle from practice. In principle, all methods for deriving equations of motion are equivalent because they lead to correct descriptions of motion. And in practice, methods vary significantly as regards labor and the simplicity of the equations. There existed a widespread belief that the choice of method was nothing more than a matter of personal taste. So this article came out in 1986 and it raised hackles in academia, but the genie was out of the bottle. And if you don't believe me, when you have time, type Kane dynamics or Kane's method in Google and see how many hundreds of references there are to it. Now, how does one judge a method for formulating equations of motion? Well, labor and simplicity. How much labor do you have to exert to get the equations, and how simple are they when you get them? You know, are they 10,000 lines long, or are they only 100 lines long? And these are the only legitimate criteria for judging them. Now, here's an artist drawing from that magazine article. It's called Encounter Across the Centuries. Thomas Kane chances to meet Sir Isaac Newton, left at French mathematician Joseph Louis Lagrange, the two giants of classical mechanics. They discuss the movements of a hypothetical linkage for the space shuttle. Newton and Lagrange describing its motion using the traditional mathematics most dynamicists still employ, Kane using his methods. The two old masters are suspicious when they see that Kane has eliminated better than 75% of their math. Now, here's how I got my start as a dynamicist. What got me interested in the subject? Well, sophomore year in the spring semester of 1970, I took a required introductory dynamics course. So, now, some of you have taken such a course, right? And the book we used was, we had a mediocre instructor, a poorly written textbook, and clumsy mathematical notation. So you can imagine this is an unlikely way for me to get interested in dynamics. But what happened is, if you look on page 521, is that, I think it's, yeah, or 507, there's equation 1521. I blew it up for you, I retyped it. And it's written in really clumsy notation, which I would never use today. But it caught my eye because up until then, I'd only had freshman physics where all the mechanics problems are with particles and they're all in a plane. And they're really kind of boring. But this let me calculate acceleration of a bug crawling up an arm on a crane that's moving around and going up and down, doing everything. All I had to do was learn how to make each of those terms. And you put it together and you get this big, huge vector, and it's very straightforward. I said, hey, this is really cool. And the other thing I noticed was down here, and I blew that up for you. It says, although equation 1521 may seem somewhat terrifying at first, you will find that by using it, problems would otherwise be tremendously difficult could be readily carried out in a systematic manner. So I thought, hey, this is really something. And also, even though this was a bad book, I thought this is probably the only engineering textbook in the world that had the word terrifying in it. You know, I thought this is really cool. Well, that got me all excited. You know, if all you do is learn how to evaluate these terms, and you can do all these really hairy kinematical things. You know, they never told us that in freshman physics. So before I graduated, I took intermediate dynamics. This was elementary dynamics or introductory. And I took intermediate dynamics, advanced dynamics, space flight mechanics, stability of motion, and dynamics and control of artificial satellites. As well as an undergraduate. I mean, I just took everything they had. I thought this was really neat stuff. And then I went to grad school and I began a long association with Kane in the fall of 1972. And we collaborated on many things. And one of them being this paper, which is kind of famous because it destroyed the credibility of those making the claim that the choice of method for formulating equations of motion was nothing more than a matter of personal taste. Using the same complex example problem, this paper compared 7 methods as regard labor and simplicity, our 2 criteria. And we showed beyond a shadow of a doubt that Kane's method came out unequivocally superior based on these criteria. There were no opinions here. We just we took every method at face value and just carried out the steps it required and showed that they either got huge equations or unnecessary labor or both. So this really made a big difference. But even with Kane's method, formulating equations of motion by hand is a tedious, time-consuming process. So the question is, could one speed up the process of formulating equations of motion by orders of magnitude using computerized symbol manipulation? Well, when I was at the University of Texas, I got to talking to some of these orbital mechanics people who did all their perturbation stuff. They were writing these computer programs that did algebra on the computer, not arithmetic, but algebra. And they evaluated these huge expressions for perturbations. Well, I said, well, why can't I apply that to Kane's method not to solve the equations like the orbit equations, which are pretty simple, like the orbits people were doing, but to derive the equations with Kane's method because it's such a simple algorithm. So I made sort of I wrote this paper, and in the paper it is shown how the symbolic manipulation language format can be used in conjunction with Kane's equations to generate on a digital computer explicit equations of motion for given multiple rigid body systems. And it was a proof of concept. I just wanted to prove it. That's all I did, was just show it could be done, and it got published. It was that, in those days, it was kind of significant. So here's the example I did. You have 2 bodies. The big one, B, is a body with a little body R, like a rotor, and it spins around this axis right here, right there. It's like a hinge, it just has 1 degree of freedom. It can go around in a circle. And I wanted to write the equations of motion of that. Well, so I programmed Kane's method into format, and I got this. It had 7 degrees of freedom. The big body has 6, 3 translational, 3 rotational, and the rotor has 1 rotational degree of freedom relative to the big body. So that's a total of 7. And so there, the equations in matrix form look like that. And the X matrix is on the left, and then the 7x1 Y matrix is on the right. Now, that's what for Lagrange's method, it would have been 3 or 4 times as many terms, because you would have had to put the Euler angles into the attitude motion to use the Lagrange method. Now, if you take out the rotor, you get 6 equations because that degree of freedom goes away, and everybody's familiar with this, Newton's second law and Euler's equations for a single rigid body. But you put the rotor back in, and you see it goes up geometrically. So in the space business, we have things that are much more complicated than this, and you could have thousands and thousands of lines, and so symbol manipulation is indispensable. Because you can see that makes a big difference. This is what you see in your dynamics course. This is what you encounter in industry or worse. So that's that. And so the moral of the story is multi-body systems have complicated equations of motion, and computerized symbol manipulation is ideal for formulating explicit equations of motion for multi-body systems. And then we got, there's a program we wrote later. An office mate of mine, David Schechter, and I developed this interactive computerized symbolic dynamics for the dynamicist, which we could do on a personal computer, which didn't exist at the time. When I did that stuff with Formac, we used punch cards. You know, there wasn't, we didn't even have monitor. We had Schechter programmed Keynes method on Commodore 64 in BASIC. And we were able to derive all of these equations much more conveniently. The computerized symbol manipulation was a good idea, but Formac, the language itself, took up too much computer memory, and Formac executed instructions too slowly. And this limited the number of bodies one could accommodate with Formac. And there's a long, I won't spend the time now, but there's a long story about how it got to be named AutoLev, which stands for automatic or automated Levinson. But anyway, so we published a paper on how you could apply this to spacecraft dynamics, and it demonstrated the effectiveness of AutoLev by using it to formulate the equations of motion of a 7-body spacecraft possessing 14 degrees of freedom. And you saw what a 7 degree of freedom system with 2 bodies looked like. This was really quite an accomplishment. And then I got the idea to apply it to robotics. I worked at Lockheed at the time, and I published this AIAA paper at a conference, and where I did the kinematics of this robot. And here's the robot. It's huge. It was called R²X, but I called it SIR. You know, it was pretty big. It was like 7 feet tall. But anyway, and then Kane and I published an article on this in the Multibody Systems Handbook. The editor had issued sort of a challenge to all these people to use whatever computer programs they had to solve a bunch of challenge problems. He gave us, say, 3, I think there were 3 problems. And we applied AutoLev to this, all of them, successfully to get a simulation. And here's what I thought you might think is interesting. This is a linkage. Whoops, what just happened here? This is a linkage. This is the input crank. This crank gets turned around, and then the whole thing moves. And the idea is to calculate the time histories of all of those angles. And it was very easy to do. We were able to do it with AutoLev without any trouble. And they published all the solutions of all the problems in this handbook. And then Kane said, hey, you know, maybe we can teach mechanics, not just use it to do it, but we can actually teach it. So he and I wrote this paper, and then we wrote some textbooks where we tried to teach undergraduate mechanics at Stanford with AutoLev, so we could give them more interesting homework problems. You know, the problems weren't just real simple. We could give them some really hairy ones and it wouldn't bother them. And then you could do stability analysis. You know, here's an n-tuple pendulum hanging straight down, and the body A at the top is rotating about the vertical. And if you bump it, do the pendulum go flying off every which way, or does it just sit there and vibrate? You could do a stability analysis of that with AutoLev. And so what follows, there are some examples of things that are not hard to do if one knows how to formulate equations of motion. Now, this you could do by hand. Here's what's called a plate pendulum. The body A is a rod that swings back and forth on a revolute joint like a pendulum, and attached to it is a plate that can spin about the axis of the rod. So it's a 2 degree of freedom system. Now, what you can do with this is, I pressed the wrong button. You can, first you derive the equations of motion. I use Keynes method, so it's pretty straightforward. So here are the equations of motion. And if you pull the rod aside and you give Q1 an initial value, so it's 40, you make it 45 degrees. You're right here, Q1 at time 0, you make this angle right here 45 degrees. And then you make this angle 1 degree, and you release it from rest. You see it just oscillates back and forth between plus and minus 1 degree, the plate. It just, the rod swings back and forth between plus 45 and minus 45. The plate just goes back and forth. So what happens now, if instead of at 45 degrees, you make it 90, you know, so here I'm starting the rod out horizontally, and then, but making this angle still 1 degree, you can see the plate goes wild, you know, it spins at many degrees, you know, it spins around a lot. You say, well, I see what's happening. If I give it a small angle, it just does a little bit of vibrating. But if I give it a big one, it goes crazy. But then if you give it an even bigger one, 135 degrees, it goes back to the other one. And then if you make it even bigger, like 175 degrees, it makes the large motion. So this is a very interesting system, which you can study if you can write equations of motion. And then here's something I did on a, I don't know, kind of a bet. There's a challenge. One guy at work saw them demonstrate this on Mythbusters. If you take two Coke cans, the tan circles, or imagine those are the ends of cans, you lay a board on top of it, and you take two metronomes, like when you learn piano, and you stick them on the board, and you set them in motion with different starting angles. The Mythbusters showed that they actually self-synchronize. And it doesn't matter how many there are. You can put them all, but if you eventually they will all be in sync. And if there's still time and people want to see it, I'll show you an animation of that at the end, which is the solution of these equations, which I derived. Now, here's what happens. You see the red line is this pendulum, and it starts off at 40 degrees. And the blue one starts off at 5 degrees. And then but they both have the same period. And you can see that the red and blue curves are out of whack until the right-hand portion, when the blue curve is right on top of the red one, so you can't see it. They've synced up. And if we have time, I'll show you the animation. You can actually watch it happen. But these are kinds of things you can do for your amusement, but you can also do really cool stuff in the space business and get paid. So now, we realized in the 1970s that we needed better visualization of simulation outputs than that provided by plotting curves. And there weren't any such thing as computer graphics. So I said, well, why can't I make something simple? I said, imagine that there's an object behind the screen S, and I'm just looking at it through the screen, and I could look at its projection on the screen and do all the kinematics of what must be happening on the screen, the X and the Y, based on what it was really doing there. And then I could remove hidden lines if it were just a box. So I worked all of that out. And here's a simulation of an unstable maximum axis spin of a spacecraft that I did back then. And not knowing anything about computer graphics, just plotting these things using kinematics. But later, people have developed all kinds of sophisticated animation things. And here's a program that works, it's compatible with Autolev, that takes the Autolev output and animates it. So now I'm just going to quickly go about what's the difference between animation and a cartoon. And you input a complete description of geometric and inertial properties of the system, and you have a complete description of the certain forces acting on the system. And you make a complete description of the motion of the system at time t equals 0. That's our initial value problem. This is what an animation of a simulation. And then we formulate and solve the differential equations of motion. And we output a description of the motion of the system for time t greater than 0. And then we animate both the input and the output. So that's what an animation is. That's not a cartoon. A cartoon is different. Cartoon is we input a complete description of the geometric properties of the system, but not the inertial properties. We input a complete description of the motion, not just at t equals 0, but at t greater than or equal to 0. The whole motion of a cartoon is input. And even if the motion violates the laws of physics, I'm sure you've all seen cartoon characters that run off a cliff and they don't fall until they realize they're not standing on anything. And then out of nowhere, they pull out a sign that says, oops. And as soon as they pull out the sign, then they fall. Well, that doesn't happen in real life, but it happens in cartoons because that's input. And so there's no output. And a cartoon is animation of input. So animations that you get from simulations are this upper one, not the lower one. So anyway, if there's time, we'll go that. And I'm almost done here. The typical undergraduate dynamics course content looks like that. I think that'll ring a bell with most of you. That looks like what your book is. I didn't take it from any book. It's just every undergraduate mechanics book looks like that. And it fails to teach the skills needed to formulate equations of motion effectively. You get something like this. See, this is the same list, but it gives the students a false impression that dynamics is a confusing hodgepodge of ideas, and it's unfocused with lots of jumping back and forth between topics. For example, we have kinematics, kinetics, kinematics, kinetics, kinematics, kinetics, kinematics, kinetics, right? We're jumping around. Vectorial energy, vectorial energy, vectorial energy, right? This looks familiar. And then planar three-dimensional, that's all this. And it looks like mostly a massive collection of clever tricks that must be memorized. And it tends to be the readout course for prospective engineering students. And it's mostly an academic subject, not very useful in real engineering. A lot of people get this impression, and it's no wonder that so many engineering students come to view dynamics with fear and loathing. So let's start off with this basic fact that dynamics is a subject that deals solely with details. You omit the details and nothing remains. Now, physicists will disagree with that. They say dynamics consists of a few simple principles and the rest is just details. But for engineers, the details is everything. And that is, Professor Kane taught me that, and I think that's one of the most important things he ever said. Now, what should be the content of an ideal undergraduate dynamics course? There are four main topics in dynamics. Now, what do I know what they are? Well, Newton told us. Now, don't think of this as a law of motion. Think of it as four subject areas. One of them is A stands for all of kinematics. M stands for mass distribution, moments of inertia, products of inertia, mass center location, anything having to do with mass. This has to do with forces and moments, couples and torques, everything. And this is how do you formulate equations of motion. So I put together what I think the ideal undergraduate dynamics course should be. There should be a kinematics chapter, a mass distribution, forces and moments, and a section on Keynes' method. But then I got to thinking, I said, that's not really enough. We need a chapter 0, but let's number them 1 through 5 instead, because most people aren't very good at vectors. And so I thought, well, we need to put in a vector analysis chapter. And that's what I think is the ideal undergraduate dynamics curriculum. So that's all I had to say. And I conclude with, may the generalized inertia force be with you. So I'd be happy to answer any questions anybody might have. Is any do we have time to see the animation of the? Would you like to see the? A question.
Yeah, I had a question. So, is there some qualitative reason for why Keynes' method comes up with simpler equations than, say, the Lagrangian method or Hamilton's method?
Yeah. You hear the question of, why does Keynes' method take less work and come up with simpler equations? Well, first of all, it gives you complete freedom in your choice of dependent variables. If you do Lagrange's equations, you have to use generalized coordinates. You have no choice. The algorithm, you take the partial derivative of the kinetic energy with respect to the q dots, take the time derivative, ordinary time derivative of that, and you subtract from that the partial derivative of the kinetic energy with respect to the generalized coordinates. The generalized coordinates are hardwired into the algorithm. So that's what leads to the complicated dynamics, because if you're doing the dynamics of a body in space, you have to introduce Euler angles to describe the orientation of the body in space, which leads to these huge equations. Whereas with Keynes' method, you don't even have to have any attitude description if you don't want to. You can do the dynamics and add the kinematics later with these short little kinematical equations. And Hamilton's is even worse because you have to invert in literal form, symbolically, an n by n matrix just to get the equations of motion, not to solve them. But I have another talk if anybody wants to invite me back on just those. The answer. I spent an hour answering that question with all the other methods. So, but if you want, I can. Let's see if I can make the animation work. Let's see. How do I? It's not getting out of this. I want to get back. There we go. Now let me find my. Oh, where is it? Where's animate? Is it hiding behind one of these things? There's a thing called animate. Yeah, it's right. It's underneath the bar. It's right. Down to the right. It's been moved. Down. It's green.
Right. That row. Right. It might be to the left of Notepad++ on the top of your screen.
Well planned. I think it's under this black thing here.
You can grab that and toggle it. Yeah.
There it is. Okay. Now, what I'm going to do is file open. Okay, so this is the one you saw the curves for. Let's hope it doesn't bomb out. But you see, I started one off at 40 degrees, the other off at 5. And the Coke cans are just, I put the bars on the Coke thing so you can see them rolling back and forth. In other words, you can't see them rotating. So just keep watching. This is, I don't make them synchronize themselves. I just, it all happens automatically. So you can see they're starting to get influenced by each other. And you can do this yourself, with an experiment. You can just put them on a board like that and just watch them. They self-synchronize. It was on MythBot. I did it with 3, and I simulated 3, and it still did it. So I guess you could do 100 of them. See? It just works all. But MythBusters weren't able to bust it because it wasn't a myth. They actually did the experiments on the show, and that was it. So are there any other questions? Yes.
First, let me send it off to Greg. Okay, I have a question, maybe related just to this. I understand this is a visualization of the solution of the dynamic system.
Right.
And so consider, simulating result, we use computers. And this consider, maybe we have a system with some very different, time scales, let's say attitude and orbit, very different. And so how do you distinguish, some instability of the dynamics and instability of the numerics?
Yeah, the question is asking if you have different time scales. Suppose you have a dispensing simulation where you're dispensing a whole bunch of spacecraft. You need to have this really fine time step to get all the details of the springs and everything pushing it off. In fact, I'm working on something like that myself at work by coincidence. And then you have something, the thing is in orbit, it takes an hour and a half to go around, which is a big time scale. How you can't just have this tiny little time step for the whole orbit. We're looking at ways to try to switch the integration step size permanently after the deployment has taken place. We're studying that right now because you want to take big time steps over the orbit, but you want very tiny, like hundredths of a second during the deployment to get all the details of the motion. So it's something that is a problem, and it's something we're working on right now because all these people are now starting to release these huge constellations, and they want to know, are they going to smack into each other 90 minutes later when they come around? But we need to get all the details to get the initial conditions right. You have to have watch these springs unfold in like a tenth of a second. So you have to have a time interval of 100th or 1000th of a second to get the simulation of the deployment correct, so that when you go to the orbit part, you're getting the right initial conditions, and you can see if they bang into each other on the. So that's a very legitimate question, and it's something that's a concern right now in industry because of all the satellite constellations that are getting released. Any other questions? Yes.
A couple online, actually.
Oh, okay. Well, could you tell me what they are?
Well, go ahead.
Oh, yeah, we'll do.
Yeah, this system.
Yeah.
Is stable. Like if you
initial conditions, sync conditions, and then let it go? Would it stay in sync, or would it come out of sync, or would it oscillate for a long period of time?
I don't know. We'd have to find some way of doing a numerical integration so the round-off error didn't accumulate first. But I don't know the answer to that. I just know that they, within the amount of time people have the patience to watch it, they always seem to sync up no matter how many of them you put on there. Can you ask me the online question?
Absolutely. So one of the questions is, was there an assumption in the simulation that Coke cans can roll without slipping?
Yes.
Another question, do the metronomes synchronize if they're started at different frequencies? And if not, what happens?
They don't. They have to have the same period. But I haven't studied it in detail. I wouldn't know what they would synchronize to. Which one would win. Mm-hmm. Maybe they picked there's a third or the average. I don't know. I think that, they have to be the same frequency.
Okay.
Yes.
Maybe I can relate it just to the previous question and also Sentinel. Okay. And so basically just to analyze the stability. Okay. Especially we definitely want to make sure it's dynamically stable. Okay. It's not some irreversible issues. And so what's your basic way just to do this, the stability analysis?
Well, there is such a thing as stability theory. And, you can actually work out, find inequalities that have to be satisfied for stability or instability in many systems. And we've shown with AutoLib, you can do it for a complicated system. And there's all kinds of theorems. There's a whole, if you go to they don't have libraries anymore, but if you look online, there's all kinds of books on stability theory that you can do. But what we do, what I tend to do is whenever I do a simulation, I check for integrals of the motion. For example, if I have a spacecraft in orbit, I can turn off all the dissipative things in the simulation. The energy should be conserved, and if there's no external torques, angular momentum should be conserved. So I can print that out, and if the angular momentum it deviates from a horizontal line, then it gives me a pretty good idea of how the numerical solution is disagreeing with the truth. So we have to do that. You can't just say, well, it comes out of the computer. It has to be right. If you say it has to be wrong, you're probably right most of the time. So you really have to be your biggest skeptic whenever Professor Kane always said is the most dangerous computer program is one that works. That produces output. He says, if it doesn't produce output, it can't lead you astray. But once it starts producing output, then you're in big trouble because you really have to test it to make sure it's not giving you garbage. So that's it. Any other questions? Huh? Oh, yeah.
So going way back to Newton and Descartes,
He
said inverse square forces, action at a distance. And Descartes said, no, that's ridiculous. There's the swirling vortex, so it reaches out and touches the planet. But I think they gave different answers. Or do you know, would Descartes get ellipses also? Or would he get different answers with his theory?
I don't know if he took it that far. In fact, he came, he was sort of ahead earlier than Newton with what he did. So Newton would have, he didn't have the benefit of Newtonian mechanics to do what he did. It's kind of, that's why Galileo is so famous. He did all that analysis of falling bodies without equations of motion. He did it all with geometry, and he got the right answer. He was absolutely brilliant. It was, if you read that book, the Dialogues on Two New Sciences, which I think you could get on. I just read it a few months ago, but it's really amazing the proofs he does with geometry to show how you can calculate what falling bodies will do. Now, what he did is he didn't know little g, the local gravitational acceleration, the 9.8 meters per second squared. He didn't know that. So he had to find some way of comparing things. So he created this thing called the sublimity. he said, well, if we want to give it a horizontal velocity, we don't want to use velocity. We want to use something that's a distance, because a projectile has two distances, the altitude and the distance it travels. So how do you initialize it with something that's a distance? He said, well, suppose you drop the particle, and when it reaches the velocity you want to start it with, it immediately changes at right angles and goes that way. And he called that third distance a sublimity. So every initial value had a sublimity, which was the height at which you had to drop it. And as it accelerated, it would get to the velocity you wanted to, and then he would just give that the initial value. So, you know, he had the distance, you know, the trajectory distance, the altitude, and the sublimity. And I checked it all, and you know, he didn't have a calculator or anything, but we agreed at like 3 decimal places. You know, I worked it all out with. I cheated. I used a computer, but it's, you know, he's right. It's really amazing.
Is AutoLab still like a program that you use?
I still use it, but it's been superseded by something more compatible with use. There's a company called Motion Genesis that has Paul Mitiggy owns the company, and he has made the successor to AutoLab. He helped develop it at the later. It's no longer in BASIC. It was written in C++, the latest version of AutoLab, but we gave him the right to do with it whatever he wants, as long as we retained the right to do anything we wanted to with AutoLab. Now, we won't sue him for using AutoLab stuff to make Motion Genesis, and he won't sue us for using AutoLab. So I still use it at work because, you know, it was developed in the late 1980s. I'm really familiar with it, and I can do all kinds of cool stuff with it. But if you want to get it, you can get a student version for less money than the industrial strength one. Just look on the internet. Mitiggy is spelled M-I-T-I-G-U-Y, and the company is Motion Genesis. But that's, you'll like it better than AutoLab, because AutoLab doesn't look at all like computeries. It looks like the way you would do dynamics by hand, but you just type things. You know, there's no menus. You know, you have to type something, or it just sits there and stares at you. You know, but I think Motion Genesis is more like the kind of software you're used to. But it does the same thing. It's all based on Kane's method. Mitiggy was, I think, Kane's last graduate student, and so Kane would have been, he would have been like 99 or something if he'd lived. So that was a long time ago. But the AutoLab is, you know, it's no longer marketed. I just happen to have a copy that I have the rights to. I use it at work all the time. In fact, I think Maxar owns 2 copies they bought 40 years ago, and I'm using one of them. But I have my own copy right here on this machine.
Did you work under Kane as grad student, or did you
learn independently? Yeah, well, I was his student, and then after I left, he and I collaborated for years. You know, we wrote dozens of papers and books and stuff together because we just work well together. And yeah, so I would say I spent a lot more time with him after I left than while I was there. So, and huh?
Thank you for your answers.
Oh, that's okay. I got lots more. You got any more questions? You got.
Out of curiosity, how widely taught is Kane's method, and how popular is it in industry?
Well, it's unfortunate that it's not widely taught. I'll give you an example. Mitiggy, while he works for Toyota, was teaching part-time at Stanford in the mechanical engineering department. And he taught the dynamics course the way Kane would have taught it, although they reduced it from 3 academic quarters to 2. Kane used to teach a 3 academic quarter graduate course in dynamics, had over 100 students in it. It's like freshman chemistry. I mean, people came from all over to take that course, and for budget reasons, they cut him down to 2. Well, he won the best teaching award 3 consecutive years at Stanford, even though he was only a part-time instructor. And they for some technical reason, they canceled dynamics at Stanford, and he's still teaching the undergraduates, but the graduate level course is no more. Stanford must have the only mechanical engineering department in the entire world that doesn't have a dynamics course. And he won the teaching award 3 consecutive years teaching this material, and they abandoned it at Stanford. And I don't know where else they do teach it, because, you know, the people who are best qualified to teach are Kane's former students. And as you can see, that we're all getting kind of old. We all have, Kane had a Kane number of 0, and we all had Kane numbers of 1. And professors who had Kane numbers of 1 would have, their students would have Kane numbers of 2, but it didn't branch out. You know, they don't teach it all that much. But, you know, in a sense, that's good for people like me, because at my advanced age, they still hire me to do all these things that other people can't do. It's amazing. You know, people say, well, how do you do dynamics like that? And I said, well, I explain it to them. That's this method. Oh, it can't be. You must be really smart. I said, no, I'm not smart. This is method. And it's, you know, it's like telling them the secret and holding it right in front of them. They just don't buy it because they've never tried to do these really complex problems. But if you learn Kane's method, you can do, it's almost like magic. You know, it's really is. It's a, yes.
What instrument did Tycho and Kepler use to come up with such accurate orbital equations of motion?
Well, Tycho didn't even have a telescope. He used, I don't know, astrolabes and things. But the thing, I'm not sure exactly. They were his own inventions. But Kepler, he didn't really use the Tycho. He used Tycho's data, which were more accurate. I don't think Kepler actually got out there and did much observational astronomy himself. He might have helped Tycho because he was his assistant. But I think what really happened is that he just had this really accurate numbers that dealt with the most elliptic orbit in the solar system, which is the orbit of Mars. And those two together enabled him to figure out the Kepler's 3 laws, which in turn led Newton to figure out which forces needed to make them. You know, that's why the scientific revolution was so amazing, is that about 144 years, you had all these really smart people. If any one of them had been missing, the whole thing would have collapsed. And they all sort of fed off of each other. And it never happened anywhere else in the world. It was just a singular, very small geographic area, and a very short period of time as far as the human existence is concerned. It's really quite a miracle, if you ask me. Yes.
Sorry, I know that we are almost running out of time. So you have 2 books, Dynamics Theory and Application, with Dr. Kane, and also Spacecraft Dynamics with Dr. Kane and
Likens, Peter Likens.
Yeah, Peter Likens. So both books are out of print. For those of us that, or the audience that might be interested, is there any way that we can get a electronic or soft copy of it?
And it's free.
Is it, where is the
Cornell? We gave Cornell permission. They take out of print books, and if the authors agree, they print them up. Well, they make photocopies. I mean, they're not the greatest copies in the world, but it's free. Okay. So you can go, if you look at Cornell, you type Cornell and the name of the book, you can go to the site and you can actually download a PDF of a photocopy of both of those books. So it's free. I think they'll send you a hard copy of the photocopy for a small fee, but you can get the PDF on the house.
Okay, thank you.
I kind of want to piggyback off of that. I actually have a copy. Would you be willing to sign it?
Sure. Oh, yeah. Do you have a pen? I didn't bring one. Okay. Any other
questions?
Yes.
I have maybe more one observation than a question. When you're explaining or talking about Kane's method, for somebody who is venturing into the field that is not a seasoned dynamicist, kind of gets the feeling that the method is somehow liberated from the fundamental laws of motion, like the Newtonian one and so forth.
Well, no, actually, it's what the difference between Kane's method and Newtonian mechanics is that you don't have to draw free body diagrams of where the non-working interbody forces, you have to introduce them and then algebraically eliminate them. And for example, if you had a simple pendulum, there's a horizontal and a vertical force component holding the pendulum from falling. Now, if you write the equation of motion of a pendulum, those 2 force components don't appear in the equation. Those are because they're what's called non-contributing forces. You can back them out. You can find out what they are. They're functions of time. But in Newton's mechanics, you have to draw all these free body diagrams and put all these forces in, and they have to eliminate them algebraically, whereas Keynes' method, you don't even have to introduce them. It just gets the equations without them. And Keynes' method is based mostly on vector algebra, dot products. You take dot products of things called partial velocities and partial angular velocities, which Keynes discovered, with ordinary forces and accelerations and moments and angular accelerations, and you get the equations of motion. It's just bingo. It just falls out.
But it is fundamentally based
on real basic stuff. Very basic. Yeah, it doesn't involve virtual work or kinetic energy or, or generalized momenta. It's all really fundamental stuff that you learn how to do in school. And you just take dot products of these partial velocities with those fundamental things, and out come the FR and the FR star.
Yes. And
then you add them, and that's the equation of motion for the Rth one. Yes.
Is Keynes' method exact, or is it like approximate?
No, it's exact.
Okay.
Gives you the exact nonlinear equations of motion. Now, the interesting thing is if you want linearized equations of motion, it's easier to use Keynes' method to derive them directly without going to the nonlinear ones first and then linearize them. You can, and you can do it with much less work than you can with energy methods. You can get the linearized equations for control theory or stability analysis without ever doing the nonlinear ones first.
And there's no limitations to Keynes.
No, it's just, well, you can read that the papers we've done where we point that out. Of course,
the limitation is your patience on writing out.
Yeah, well, even with Keynes' method, dynamics is tricky. It's a laborious business. You saw it with just two bodies, how big it got. Lagrange, it would be 3 or 4 times as big. But if you use a symbol manipulation, you can have the best of all worlds. Because it's easy to code. It's easy to take a dot product with a symbol manipulator. To extract the coefficient of something in virtual work is a lot harder because it's hard to form virtual work. It's too vague. Yes?
Is the method limited if the motion or the equations are dependent on time?
What?
Like you have a time variable on the equation. The method limited coming up with equations of motions that are that nature.
No, I've seen it, where you can eliminate time, you can replace, with angles or distances as the independent variable. But mostly the kind of stuff you deal with involves time, and it's really designed around that. But I've seen people using it to, write equations where the independent variable is not time, but an angle or a distance.
But for constant mass. Constant.
Well, there
and the mass can have a constant. There could be another variable that will be changing with time.
Yeah. Oh, yeah. You can have prescribed motions of time in the equations. The partial velocities segregate the explicit part. Explicit functions of time from the parts that are implicit. It can be done. But there's been a lot of work done on applying Keynes' equations of motion to variable mass systems. There was a professor named Fidelis Eke at UC Davis who got his PhD with Keynes, and he unfortunately died recently, but he has published quite a bit on applying Keynes' method to variable mass systems like rockets and things. So his last name is spelled E-K-E, Fidelis Eke. So you could look that up. And everybody liked him too. He was a really nice guy. In fact, you got time to tell a quick story? Yeah. When I was, one time he called me at work and he says he was trying to teach Keynes' method at UC Davis and they wouldn't let him. And he wanted me to come up there and straighten them out. And so I was a lot younger and more formidable looking in those days. But I went up there. I said, I will come on one condition. And he says, what? I says, you got to give me a free donut. And he says, so done. You know. So I drove up to Davis, and I had this big room, like 100 students, and the whole faculty were there. And they had this sort of a cult at Davis. They probably still do, where they do something called bond graphs. And they had all the students here, they wanted them to do bond graphs. And Fidelis wanted to teach them Keynes' method. So I got up there and I gave a lecture where I just compared Keynes' method to Lagrange's method, just wiped out Lagrange. And then during the question and answer period, if I remember the professors, if I had written the questions for the professors to ask me to make them look really dumb, I couldn't have done a better job than they did on their own. And it was really kind of neat because all the faculty members except Fidelis were frowning and all the grad students were smiling, you know, because, hey, this is a really neat method, you know. And so anyway, I went back home with my donut, and the next day I got a call from Fidelis, and he says the administration relented and they're standing in line outside my office to sign up for the course in Keynes dynamics, which they're now letting me teach. So I didn't pull any punches. I went up there to earn my donut, and I just left. I took no prisoners. You know, I can do that. You know, I'm like have gun will travel. You know, paladin. I will do that. You guys, it was a cowboy Western show about this guy who. Never mind.
I remember.
Okay. Any other guests?
I just want to add that your advanced dynamics course that we have at Santa Clara, we are covering Keynes method. It's a part of that. Just
okay. See, so you should all go to school here, right? Well, you do, right? Anything? Yes.
Go back to your comments on astrology. I think most of the astronomical symbols we use for planets and photo mechanics is actually taken from astrology. Right? Yeah,
they use them on, the astronomers use those as subscripts on their variables. You know, they'll like an X for Mars, they'll use the symbol for Mars as a subscript on the variable. You know, that kind of a thing. Anybody else?
All right, well, please help me thank Dr. Levinson.